Alright, welcome back to Diapsid Evolution Part 2. We're going to focus now solely on the dinosaurs. The dinosaur radiation really comes into the late Triassic. So there weren't dinosaurs in the earliest of the Triassic. The first groups really show up about the middle, and these were all small bipedal carnivores. There's a typical trend for earlier lineages to be a little bit smaller than later groups, so that follows true with dinosaurs. So there's a transition to upright posture. Now there's a couple of things that make a dinosaur a dinosaur. First, they're going to walk on their toes. Second, they're going to walk with their limbs under the body. We see Archosaur evolution coming from a stance like that on the left. So if you put your hands out to your sides, all right, that's kind of like how a lizard walks. And then slowly with Archosaurs, we're going to see them moving directly under the body. So right now I'm putting my arms out to the side and then moving them under the body, all right, straight out in front of me essentially. Remember, we're bipedal, our orientations are flipped. We see that motion happening through time, all right. Lizards have a very sprawled out stance that actually affects their breathing. So one of the reasons why that happens, it's called buccal lungs or buccal pumping, is when lizards have their arms out to the side of their body. If you will, please put your arms out to the side with me, all right, and kind of move back and forth, kind of like how a lizard walks, all right, and notice you're scrunching up your sides a lot. Lizards don't have the same muscles that you do, so when they're doing that, they're actually forcing all the air out of their lungs and they can't breathe in properly. This means that they have to stop a lot and then move again. So if you watch a lizard, it runs for a few feet and then stops, runs for a few feet and then stops. That's why it can't breathe. So when we start to move our limbs under the body, we're releasing a lot of that pressure. Mammals and reptiles are going to do that differently. Mammals are going to do it by evolving a diaphragm, right, to support those lungs, and we're going to actually put some other spaces in between it with our rib muscles. Other reptiles, diapsids, are going to actually move their limbs under the body to kind of get away from that. So dinosaurs have the limbs straight under the body. They also have a third feature, and that's going to be called the acetabulum, otherwise known as the hip socket here. A giant hole in the hip socket. It kind of looks like a soup can, or where you would put a soup can. I guess it would fit in nicely, right? Make that nice wedge. And what that does is it essentially limits the movement of the leg to a front to back, no side to side motion there. Now, how do we know this? One of the things that we can actually know is that muscle scars attach to the legs, so we can reconstruct a lot of the gait, even if a lot of the skeleton is missing from this. Dinosaurs have two types of hips. We do not yet know if the two types of hips represent synapomorphies, so group-defining features, or if it's homoplasy, meaning evolved more than once through time. And we'll talk about why that is in a little bit. But first, we'll just talk about the Saurischian and the Ornithischian hips. All right, so the Ornithischian is bird-hipped. The Saurischian is lizard-hipped. Funnily enough, the Saurischians actually give rise to birds. But what we see here, the Saurischian hip is a triradiate pelvis. We have the three pelvic bones, the ilium, the ischium, and the pubis bone, all pointing in three separate directions. All right. What we see here in the Ornithischian is we actually have the pubis bone rotated backwards. Do you see how it's been rotated backwards? As opposed to this, it's the red bone here. I'm pointing to it in case red is not your color. All right. And we see that it's actually pointed backwards. And that will be really important for understanding movement in a little bit. So here's the traditional dinosaur phylogeny. This is what we have been taught for, I don't even know how many decades, possibly even a century. We have the Ornithischians here as the sister group to the Saurischians. So Ornithischians are going to be things like our duck-billed dinosaurs, Triceratops, Stegosaurus, and the Saurischians here, the triradiate hip, have two groups, the sauropods, the long necks, and the theropods, like T-Rex. That's our traditional phylogeny. However, recently, one scientific paper seems to have thrown a lot of that out the window. And that would put the sauropods as a sister group to a new group called the Ornithoscelida, And that would mean that lizard hips actually evolved more than once in sauropods and theropods, making it homoplastic. We don't fully know if this new tree is the real tree. However, a lot of scientific studies have been thrown at it to show that it actually has a lot of validity to it. So this was published in Barron et al. 2017. So what this could mean is that the theropods exited themselves from the Saurischians T-Rexiting themselves from the situation. Ha. All right, so when it gets accepted for publication, that doesn't mean it's been accepted in the scientific community. Remember that we always have to reevaluate data over and over and over again. If your hypothesis is sound and you have your data interpretation, then it gets accepted. Then other folks will start to test your hypotheses. So far it seems to be holding up, but that doesn't mean we need to throw out all of our getting rid of all of our textbooks and things like that just yet. All right, so we're going to talk about the groups in their original groupings. We're going to talk about the sauropods, we'll talk about the theropods, and we'll talk about the ornithischians. Now, whether or not sauropods and theropods belong in a larger group called saurischians, or if ornithischians and theropods belong in the ornithoscelida, we don't know. So we're just going to talk about the three groups kind of separately. So the sauropods are an herbivorous dinosaur group. They're massive. They peaked in size and diversity in the Jurassic. Most were quadrupedal, pretty much all of them, and they're known for their long necks and the ability to achieve enormous sizes, absolutely gigantic, which brings up a lot of questions about their biology. So here's some diversity here. We see just the bittiest of them were bipedal. A large diversity of these organisms have recently been found in South America, such as Argentina, in the Patagonian section, and Brazil and places like that. It's where a lot of the famous dinosaurs are being found. They have peg-like teeth, and they really did not chew. They swallowed their food whole. They used their teeth to kind of strip leaves off of things, and they would let it ferment in their large gut. Long necks gave them access to a large feeding area without having to move too much. But plants are really difficult to break down. They really are, and a lot of animals have a lot of different ways to come up with ways to break them down. So because they're not chewing, they've got to break it down completely in their gut, So how they would do this is they likely swallowed rocks to help, much like modern day birds will actually swallow gravel to help them digest food. These are called gastroliths, literally translating to the stomach, gastro, lith, stone, the stomach stones. All right, so this likely helped them break down a lot of that plant material. So this was, if you think about cows today, cows spend a lot of time chewing their food, that plant material, and then that plant material is passed through multiple stomachs. Rabbits, on the other hand, will actually just chew their food once, and as they chew, they'll break it down, they will excrete their waste, and there is actually some of their waste that they will eat again. This is called their cecotrophs. It's just nutrient-packed stuff. It's not dangerous to eat. They eat it again to break down even more of the nutrients. So plants are pretty difficult to eat. Got to come up with a lot of different ways to get around it. Some sauropods actually underwent island dwarfism due to being separated onto a smaller area. So we've got an example here of a sauropod that was only 18 feet long, all right, 6 meters. So here is a fun example of one of the largest pterosaurs potentially picking up a small little bitty sauropod for a meal. We talked about this in trace fossils, but I wanted to bring it back. Here is a sauropod urolite, so what the trace the sauropod would have made going to the bathroom. All right, the ornithischians. A stunning amount of diversity. All herbivores. They could be quadrupedal or bipedal. And we'll talk more about how we can determine their gait in a little bit. So these are broken down into a number of different groups, like the thyreophorans. These are going to be our armored dinosaurs. And then into the ceropods, which have an expanded shelf at the back of the head, right? What we see here with the ceratops and other things. They have dental batteries. So these dinosaurs are herbivorous, but they didn't grow to the immense size that sauropods did. And they didn't swallow rocks as far as we know. So they have to have other ways of coming up with chewing. All right, so what they would do is they grow these dental batteries. These are like teeth, and they have evidence of cheeks. So they would actually they would actually have these teeth in their cheeks called cheek teeth, and their jaws could actually move side to side. So if you will, move your jaw side to side for me. All right, move it side to side and then up and down. You'll notice up and down is a lot easier, right? It's a lot easier, and the reason for that is our jaws really were not evolved to go side to side. We have bones that really don't want us to move that way. Ornithischians actually have a special bone that allows them to make that movement more comfortably. So this is Edmontosaurus. This is a duck-billed dinosaur, the only dinosaur fossil ever found in Tennessee thus far. The more you know. All right. So why is that important? Why do we care about how they're chewing? And what does this have to do with the hips? Good question. Ornithischians are bipedal or quadrupedal. They need a lot of space to break down the food. A lot of it does take place in the mouth, which means they don't have to evolve these massive stomachs like saurischians did, like the sauropods, but still got to have a lot of room for intestines. So what we do is if we rotate this pubis bone backwards, note here, remember it's rotated backwards, we're actually making space for a little bit extra intestinal room. It allows them to have a large gut for digesting plants, but also allowing them to take an upright stance. So having that backwards turned pubis is really important for allowing them to eat plants. Ornithischian teeth and jaws. A lot of different adaptations in the teeth for eating plants. We have teeth for grabbing and that are a little bit sharper, and we have duller ones for grinding. Here we have the bone that's going to allow the side-to-side motion back here. We have the cheek teeth, here called the chisel teeth. There's a sharp beak for grabbing. All right, so those are the adaptations for organisms eating plants in the ornithischians. Let's talk a little bit about Stegosaurus. All right, a lot of folks think that the plates on the back of the Stegosaurus are for defense, but they're actually quite thin and filled with blood vessels, indicating they're actually for thermal regulation. Some folks thought maybe they were for sexual selection. We don't think that that's the case anymore. So Stegosaurus, as far as we know, have never been found in adult pairs, male-female pairs. They have been found in parent-child pairs. And really, we haven't been able to find evidence of sexual dimorphism, meaning differences between the males and females. That's an interesting thing. Now, some evidence as of 2019, 2020 may change what we know about this. We're not sure yet, so bear with me, this might change. But usually, what we can learn about sexual dimorphism, all right, di means two, morph means shape, all right, so shape between males and females. There are more than two sexes in the animal kingdom, all right, there really are, so snails are a really great example of that. Fish, some fish can switch between male and female with ease, as can snails and other groups. So don't put too much emphasis on the word dimorph, okay? But typically, invertebrates, especially with mammals and larger reptiles, we see that the more competition for mates, the more dimorphism there will be. Here we have the elephant seals. The male is on the left. All right, he is the one smiling at you with a face you wish he wasn't smiling at you with. And the lady is on the right. So elephant seals are super mean. Elephant seals have extremely high sexual dimorphism and extremely high competition for mates. Males will actually fight to the death to make sure that they have the mates that they want. All right? So, high sexual dimorphism. Do humans exhibit sexual dimorphism? They do. Typically not as much, especially not as the elephant seals. We'll talk more about that during our next lecture. So Stegosaurus doesn't have much sexual dimorphism. What does that mean? Well, it likely means there may not have been a lot of competition. It could mean that Stegosaurus likely did not spend exorbitant amounts of time with partners. Pachycephalosaurus. Here's a cutie right here. So what is this giant dome for? A lot of ideas have come about. Was it sexual selection? Were the males evolving these large domes and females were like, hey, that dome seems really great. Maybe they're fun to get to know. Probably not. Not a lot of evidence for that. What about defense? Well, a lot of folks earlier thought that they would probably break their necks if they were using their heads as battering rams. But let's look at the evidence. 22% of all known Pachycephalosaurus domes actually have infections resulting from traumatic injuries caused by collisions. So it actually is likely they were fighting for defense. Now, whether this was they were fighting for mates or fighting for territory, we really don't know. But the trace fossils can tell us a lot about that. So here are some examples of those healing traumatic injuries. All right, moving on to the third group here of dinosaurs, we have our theropods. Theropods have a number of different dinosaurs within them. These are typically going to be the very famous dinosaurs like T-Rex, Velociraptor, and other organisms like that. So they're all bipedal predators until you get to the more derived coelosaurs. All right, so here are coelosaurs right here. We can assume feathers go back at least to coelosaurs, if not earlier. This does mean, let's go back to that tree. This does mean that tyrannosaurs had feathers, as does most of our raptors, and of course birds today over in the Paraebes. All right. So here we have examples of some of these feathers. These are coming from Lagerstätte. That's beautiful, beautiful, beautiful fossil forming sites. Some can preserve soft tissue. These were in fact so well preserved we could get molecules out of them to see that they're made out of the same stuff that bird feathers are today. We have been able to reconstruct the color in some examples as well. Here we have quill knobs on velociraptors, so we can actually see where the feathers would have been attached. Now, as I said, some derived coelosaurs were actually not carnivores. All right, now we know that they're carnivores based on the shape of their teeth, very sharp. But we actually have this organism here. This is a derived coelosaur called the Therizinosaurus. Absolutely massive, much larger than an average human, about 3 to 4 times the height. All right, so they've got these large claws. They've got this really beautiful face that only a mother could love, and a lot of dull teeth in the back. First question, why evolution? Why? Evolution does not have an answer for us. Here is the Therizinosaurus compared to a 1.8 meter tall person, so just under 6 feet. A lot of people call this the Freddy Krueger dinosaur for very obvious reasons. All right, so we assume that it had feathers. We're not sure what those feathers would have looked like. So why is it a vegetarian? Why is it a vegetarian? So originally, scientists thought that these claws might have been weapons, right? Makes sense. Look at those things. This is probably one of my most favorite dinosaur memes. It is not funny in the slightest. I don't know why it cracks me up, but there you go. We thought that they were weapons, but scientists have lately reversed that idea, and they think that they were for stripping leaves off of the trees. They also have no sharp teeth. So this could have been an example of a lack of available resources, forcing them to kind of go into the plant and eating world. Now, birds. The first birds show up in the Jurassic. This is the famous Archaeopteryx found in the Solnhofen Lagerstätten, all right, in Germany. This was found, or the first evidence of Archaeopteryx was found not too long after Charles Darwin published On the Origin of Species, where he predicted the evidence that we would find evidence of transitional fossils, right? So we have the long stiff tail, that is the synapomorphy of the Tetnurae within theropod dinosaurs. It has feathers, it has an S-shaped neck. It has our lizard hip structure that we expect to see with theropods. It has bird and dinosaur characteristics. So how do we go from T-Rex to the chicken? Is this an example of evolution disappointing us? Not necessarily, right? If you've ever made a chicken mad, you know that they've still got the temperament of many dinosaurs, all right? So what we see is in the trend of non-bird dinosaurs to bird dinosaurs, we see a reduction in the skull and body size over time. Now, while most dinosaurs were not as large as T-Rex, of course, most were actually quite small, they do get smaller through time. And one of the things that we see is a paedomorphic trend in the skull. So if we look at Ceratosaurus to Deinonychus to Archaeopteryx, we see that the skull is getting more juvenile-like through time, all right? We also see body miniaturization. So here we have the Triassic down to the Jurassic, where we have birds getting much smaller over time. So birds are essentially paedomorphic examples of the dinosaurs that we see in our favorite movies. Now, this leads us to a question. Birds are warm-blooded. Most reptiles, though, that we've learned are cold-blooded, like lizards, turtles, alligators, crocodiles, things like that. There's actually a lot of evidence to suggest we still don't fully know. There's evidence for both. Feathers evolved a long time before flight, right? So T-Rex has feathers, and it clearly was not flying. So this suggests that they were likely endothermic, meaning warm-blooded. All right. Temperatures were likely around 36 to 38 degrees Celsius of the actual body itself, which supports endothermy as well. So there's some evidence that suggests that the bone microstructure shows that there were seasonal growth changes, which would support ectothermy. However, there's some other structures in the bone and rapid growth rates that supports endothermy. Muscle mass suggests that large bipedal dinosaurs were moving too quickly and they would need endothermic metabolism. But on the other hand, sauropods and things like that would have the issue. If they were endothermic, they would actually have too much body heat. They would probably cook themselves, right? So that's an idea called gigantothermy. So that would likely point them towards being ectothermic, cold-blooded. So the long story short is we really don't know what the metabolism of dinosaurs actually was. Could it be that they were a mix of both? This is something called tachymetabolic endothermy. Could it be that one group of dinosaurs was cold-blooded while the others were warm? There's a lot of evidence to suggest yes or maybe. We don't really know for sure. So the end of the age of the dinosaurs. A lot of folks call the Mesozoic the age of the dinosaurs, and they call the Cenozoic the age of the mammals. But I will raise the question to you, did the age of the dinosaurs ever end? Today, there's 5,400 mammal species alive, and that's compared to 9,000 to 10,000 dinosaur species, even after the KPG extinction, the asteroid impact in the Yucatan Peninsula 65 million years ago, along with the Deccan Traps volcanism at around the same time. Humans have actually fought wars to the emu. This was in Australia. You can look it up. This is real. So who says the age of the dinosaurs really ever ended? Here are our dinosaur friends. Alfred Hitchcock made a movie about how much he feared the dinosaurs. So think about that next time you see a lowly pigeon eating out of the trash can. That is a dinosaur. All right, here are your review questions. I will see you for the next installment of